folks, Ms. Gosling here. In this video, you're going to learn about net force and kinematics. By the end of the video, you'll be able to use your net force to solve kinematics problems. So let's go ahead and get started, shall we? So in this video, what we're going to be really looking at is what happens when an object is not in equilibrium. So when an object is not in equilibrium, we know that the net force is not equal to 0. So what that means is, from Newton's second law, we know that F net is equal to mass times acceleration. So what that means is that our object is accelerating. So when an object is accelerating, we know then that we can solve kinematics problems using our Suvat table. So what we're going to do with these problems is we're going to start by figuring out what our net force is. Then we're going to use that net force to figure out what our acceleration is. And finally, if we need to, we can always use that acceleration to figure out other parts of our Suvat table, as long as enough other information is given, of course. So let's go ahead and look at a pretty simple problem. So in this problem, we have a box that is initially at rest and is pulled to the right with an applied force of 10 newtons. A frictional force of 7 newtons left also acts on the box. How far will the box travel in 2 seconds? So let's go ahead and start by drawing the free body diagram for the box. So here's my box, and it is being pulled to the right with a force 10 newtons, and to the left with a force of 7 newtons. So that means that the net force on my box is only in the x direction, and it's going to equal my 10 minus 7 newtons, assuming, of course, that to the right is positive, as we usually do. So that means that the net force on my box is 3 newtons. And I realize now I forgot to give you a mass for the box. What I'm going to go ahead and assume is that my box has a mass of 1 kilogram. So let's go ahead. So my net force is 3 newtons, and I want to use that to figure out my acceleration. So I know that force net is equal to mass times acceleration. And so I know my mass, and I know my acceleration, and I know my force, and so I can find my acceleration. My net force is going to be my 3 newtons from before, and I'm going to go ahead and write that in red so that we remember. And that is going to be equal to my mass of 1 kilogram times my acceleration. So my acceleration is going to be 3 meters per second squared. Now I am ready to do my Suvat table. So I know from this problem that the initial velocity of my box is 0, since it's initially at rest. And that I have just figured out that my acceleration is 3 meters per second squared. And I want to figure out how far it travels in 2 seconds, meaning that my time is 2, and my displacement, how far, is my unknown. So my final velocity is my extraneous variable. So from this, I know that the equation I want to use is S equals ut plus 1/2 at squared, or S equals 0 times 2 plus 1/2 times 3 times 2 squared. My first term will cancel, and what I will get is that my displacement is 6 meters. So there you go, guys. That is a nice, simple F-net problem. Let's try something a little harder, shall we? In this problem, we're going to be dealing with some angled forces. So a 70 kilogram box is pulled by a 400 Newton force at an angle of 30 degrees to the horizontal. The force of kinetic friction is 75 newtons. If the box is initially at rest, how long will it take the box to accelerate to a speed of 10 meters per second? Let's go ahead and get started by drawing the free body diagram for the box. So here is my box. And what I care about is my horizontal motion, since we're going to assume that my vertical motion is constant since we're moving horizontally, we're accelerating horizontally, not vertically. So here is going to be my 30-degree applied force. And directly in the opposite direction is going to be my frictional force of 75.0 newtons. And in fact, I can also go ahead and I can label the value of this force as being 400 newtons. So my next step is, because I only care about that x direction, I'm going to go ahead and say this is positive, by the way, guys. I only want the x component of my applied force. And I know from my previous video that the x component of my applied force, so FA in the x direction, is going to be FA times the cosine of my angle, or 400 times the cosine of 30. So when I solve that out, what I'll get is that the applied force in the x direction is approximately 350 newtons. I'm rounding here, guys, just letting y'all know. So here is my force in the x direction that's applied. And I know that it's going to the left as well, so it's going to have that negative sign, since we're deciding that to the left is negative. Now I can find my net force. So F net is equal to my force in the my applied force in the x direction plus my frictional force in the x direction, giving me that F net is equal to negative 350 plus 75, or F net equals negative 275 newtons. Now I can use that to figure out my acceleration, and you guys are seeing now that this is a lot of steps, right? So I'm going to go ahead over here so I have enough space. So I know that F net is equal to mass times acceleration, or negative 275 is equal to 70 times my acceleration, giving me an acceleration of approximately negative 4 meters per second squared. Now I can plug that into my SUVOT table. I promise, guys, we are almost done. So here's my SUVOT table. My acceleration I now know is negative 4. My box is initially at rest, so my initial velocity is 0. And I want to find, and my final velocity is 10. Or in this case, actually, we're going to assume negative 10, since we are going to be going, of course, in the direction that we're accelerating in. So guys, just the thing here is making sure that the sign for your acceleration and your final velocity both match. And I want to figure out how long it will take, so what my time is. So I know that the equation I'm going to use is v is equal to u plus at, or negative 10 is equal to 0 minus 4 times my time. So my time is equal to 10 over 4, or approximately 2.5 seconds. And there we go. You have figured out how long it took the box to accelerate to a speed of 10 meters per second. So you've done an easy problem, you've done a medium problem, let's go ahead and do a spicy problem. So here we have something on the right that we call an Atwood machine. It's basically a massless pulley and a massless rope with two masses hanging from it. And it's a fun way to look at acceleration and net force. So here we're going to assume that the mass of block A is 5 kilograms, and the mass of B is 2 kilograms. We want to figure out the acceleration of the system when the blocks are released, and how long it will take for block A to fall 2 meters. So because block A is heavier than block B, I know that my system is going to accelerate towards block A. That means that I want to draw the free body diagram for my heavier block. So I want to draw the free body diagram for block A. So I know that the force of gravity on A is pulling block A down. However, there's something keeping block A from falling as quickly as it normally would. And that's that block B is pulling in that opposite direction. So we've got the force of gravity on A and the force of gravity on B. And if we take our vector right here for B, for block B, and I can't really do that very easily on here, but if I move it around my pulley, keeping it constantly parallel without spinning it, so it's always parallel to my rope, what I'll find is that when it goes over to block A, it's pointing up. So the force of gravity of B is actually the force stopping A from falling in free fall. So now I'm ready to go ahead and figure out my sum of forces. So I know that my F net is equal to the force of gravity on A plus the force of gravity on B, giving me that my net force on A is equal to 5 times negative 9.8 plus 2 times positive 9.8. And I'm flipping that negative and that positive because A is accelerating down and the force of B is pulling up. So that's just how I'm representing my directions. And what that's going to give me is that my net force is negative 29.4 newtons. So now I'm ready to finish solving A. And for A, what I can say is that my net force is equal to my mass times my acceleration. And in this case, now I know that my F net is negative 29.4 newtons. And I know that my acceleration is my unknown. But what mass do I use? Do I just use A? Do I use A and B? Well, this net force is acting on mass A and on mass B. So when A is pulled down, B is getting pulled up with it. So that means that to figure out my mass, I have to actually add the mass of block A to block B. So my mass is going to be 5.0 plus 2.0. And my acceleration is, again, still unknown. And what that's going to give me is that my acceleration here is 4.20 meters per second squared. And that is going to be my answer to part A. Now let's look at part B. So for part B, I have to figure out how long it will take for block A to fall 2 meters. So that is where we need to have our SUVAT table. So SUVAT. I know that block A is falling 2 meters, so its displacement is going to be negative 2. We're going to assume that its initial velocity is 0, and its acceleration is negative 4.2 meters per second. And you can see I dropped that negative sign here. That's important. Because we're asking for how long this whole thing will take, that means that my unknown is my time, and velocity is my extraneous variable. So I can use the equation S equals ut plus 1/2 at squared, or negative 2 is equal to 0t plus 1/2 times negative 4.2 times t squared, giving me negative 2 is equal to negative 2.1 t squared, or when I solve for t is approximately equal to 0.98 seconds. And there we go. So I know that this was a long video, but let's go ahead and talk about takeaways. So first of all, we can find the net force acting on an object by separating the x and y components of the forces acting on that object and only focusing on the part of our forces that it's unbalanced. And we can use those unbalanced net force to solve our kinematics problems. And I do want to quickly walk through the steps that we did here because we did a bunch of different problems. So for all of our problems, we started by drawing our free body diagram. Then we used our free body diagram to find our net force. And then using our net force, we found our acceleration. And we used our acceleration to find other components of SUBOT. So we used that to solve for whatever the question was asking us for. So there you have it, guys. You have learned how to solve some of our most complicated problems that you're going to be asked to solve. So go ahead, give it your best try, solve some of these on your own. Best of luck and happy solving.